like a capital K. One has a little T shape, 3 in a row and 1 in the middle.
Okay.
Anyway, there's 7 different shapes that it makes that you no more than 4 pieces that aren't just a rectangle. And it turns out that there's a total of 27 cubes that then fit together to make a 3 by 3 by 3 block. But if you go see the one, I think it's right across the hall.
I saw that, but it still just looked like a bunch of boxes.
Yeah,
I didn't manipulate it. So.
Yeah, so we need people to take it apart, and then it's a challenge how do you, given the constraint of how to join together, how to put it together.
Right. And that was invented by
Keith Hine in the 1930s. You know Hine and the Supergroups?
Yeah. So I have all the books of groups.
Yes,
Alex,
okay.
how are you
I
doing?
have several books.
Yeah.
So he was
How
a
are you
designer
feeling?
and a poet, and one of the main things he designed.
Hi everybody, it is hot out today. Maybe wearing like all black and a black sweater wasn't the greatest idea. I take it off, but it's like all sweat underneath. So, welcome to the presentation, Topology is Art and Designing an Educational Display Case. My name is Kevin Corotis, and I'll be giving this talk on work myself and Dr. Cox have been doing for about a year now. But before we talk about the project and some of these objects you see in front of here, I'd like to talk a little bit about myself. Now, in high school, I became very passionate about math. I competed on my school's math team, and I took all the math classes that my school had to offer. But despite what my coaches and my teachers were always putting on me mathematically, I was always looking for ways that I could push the limit of what I could do mathematically. And by the time I reached my senior year, I kind of exhausted all of the things that I could do with math in my high school, so I kind of turned to ceramics and, well, as a thing to occupy my time. And I quickly fell in love with it because I really like working with my hands and creating utilitarian objects or sculptural pieces out of essentially mud. And when I came to Miami, I quickly found a place in the ceramics department. And the first semester of my freshman year, I took an intro to proofs class with Dr. Cox. And one day during office hours, we were talking about kind of the parallels between math and ceramics. And we, over the course of a couple of weeks, we came up with the idea that I could design this display case that teaches people walking by in Bachelor Hall an introduction to kind of topology. And the idea behind this was that in topology, we are kind of concerned with very round, circular figures, such as the ones you see above. And I knew that this was obviously something that I could create with the pottery wheel and my clay. And we wanted to kind of start to design this display case to represent a few central themes in topology, which I'll be getting to, and we were using this display case to communicate those themes. Now, this display case that teaches those walking by topology is interesting for a number of reasons, primarily because of its intersectionality. I found that the project could represent mathematics, communication, art, design, as well as our theme of visualizing mathematics. And what I found the most intriguing things about what these pieces and like how they represent was really like how I talk about them, because there's so many different ways that I could talk about this display case or just these pieces. And I would go and I talked to many different professors throughout Miami, and what I found is that they all kind of saw my project through the eyes of their own profession. For example, my ceramics professor suggested that I not glaze these at all because it would diminish their sculptural identity, because the glossiness kind of promotes a utilitarian connotation to them. When I talked to professor of design, he suggested or wanted me to focus on the words and the sentences and the paragraphs that I use to reach those walking by. And Dr. Cox, a mathematics education professor, wanted me to focus on how I communicate certain mathematical ideas to those walking by. And when I was talking to these different professionals, at the moment I was always kind of convinced by them that what they were telling me was the truth, that their way of seeing my display case was, in fact, the true way I should think about it. But after kind of thinking by myself and talking with Dr. Cox and others, I really kind of went back to the middle of kind of just being in the middle of all these different circles, except now I was much more enlightened on the uses of this project. And that kind of insight is what I want to disseminate, or at least disseminate some of to you today. So the first theme I wanted to talk about, did I miss one? Yeah, that was the goal, okay. The first theme I wanted to talk about is homeomorphism. Now, in topology, we start to think of sets less as pools of elements and more as sets as these three-dimensional spaces. And what we're going to think about in this theme is we're going to think about two sets or spaces, and we're going to think about a function from one set to another. And we're going to make a few assumptions about these two sets or these spaces. The first assumption we're going to make is that these two sets are the function of these two sets is a bijection, which means that every point in the first space maps to a point in the second space, and every point in the second space represents some function of a point in the first space. And the second assumption that we're going to make is that the function of one space to another is continuous. And what that basically means, of course I'm generalizing as you do math, talks a lot, but basically it means that the transition between these two spaces is seamless and it doesn't really have any interruptions. And the third assumption that we're going to make about this function is that the inverse exists. And that means that if we wanted to, we could retrace our steps from the second space back through the function and end up in the first space. And what I chose to illustrate homeomorphism was the common theme that you find in topology classes, that a mug is a donut. And what you're seeing here is, in this theme is, I want you to look at the black mug donut kind of combinations. And what you're looking at is you're looking at almost frames of a mug kind of becoming a torus. And these frames are very important in what I want to kind of communicate to you today, because when you look at this, you're seeing these frames, and it's very still, obviously. But when you see these, your brain almost kind of puts them together into an animation in your head. And that animation is what I wanted to really kind of communicate to you via this display. And you can see the different properties of homeomorphism almost in this set. You can kind of see each point of the mug traveling through the set and winding up in the torus. You can see the continuity of this kind of array as this almost like this molding of this mug becoming the torus, and there's really no interruptions, or it's very fluid. And then the inverse is described simply by going the reverse direction, starting with a torus and then punching a hole in the side and making our way back all the way over to a mug. And those properties illustrate homeomorphism, and seeing those properties in this display is how I want to visualize homeomorphism. So moving on to our second theme. Oh, I forgot to keep forgetting slides here, I'm sorry. The second theme that I wanted to eliminate, well actually I'll say. The first theme kind of describes what happens if two solids are homeomorphic. In the second theme, we're going to really explore what does it mean when two solids are not homeomorphic. And to describe that, we're going to kind of draw on something that's really central to topology, and that's kind of Euler's formula. And we're going to start off with Euler's formula for a complex polyhedra, because that's kind of where this starts. And basically what Euler's formula for a complex polyhedra states is that if you add the vertices and the faces and subtract the edges, you'll always get 2. And you can try this for a cube or a tetrahedron or I dove dodecahedron, you'll always get 2. And that's cool. But what does it mean? And that means that there exists some kind of intrinsic relationship between well, not two, but between these types of shapes. We see that there's some kind of interworking between them all that kind of all brings them together, despite the fact that these are obviously very different solids. And that intrinsic relationship that I'm talking about is homeomorphism. But remember, we're talking about solids that aren't homeomorphic. So what happens if we move beyond these kind of rugged convex polyhedral shapes and into more curved surfaces such as sphere or solids that have a hole through them like a torus? And what we do is that we kind of approximate edges, faces, and vertices upon the solid that we're looking at. So I just included a picture of kind of what it would look like if we were to approximate those edges, sides, and vertices. And then we use that same formula to faces plus edges, or that Euler's identity formula to find that we actually don't get a number that is 2, we get a different number. And that kind of illustrates the idea that these solids are different because this formula gives us different numbers. But the thing that's kind of deceiving is that in topology, there's another central theme is that we can kind of distort and stretch pieces to whatever we want them to be, really, as long as we follow some of these central themes, such as like holes and stuff. And this is really interesting to our conversation, because what is this conference? This conference talks about how do we visualize math. But in topology, we really think that we can't really visualize this sphere, because this really doesn't need to be a sphere. It could be anything. I could stretch it, I could make it into a cube if I wanted. So how do I visualize a sphere if this is only one out of infinitely many shapes or identities that it could take on? And the way we visualize a sphere or a torus or a double torus is through these Euler characteristics. And these Euler characteristics help us categorize these solids when their visual identity can be possibly deceiving. So for what I did for this theme is I obviously threw a sphere, I threw a torus, and I threw a double torus. And we find that their Euler characteristics are indeed different. The sphere has an Euler characteristic 2, the torus has an Euler characteristic 0, and the double torus has an Euler characteristic -2. So the different numbers that these shapes represent is really essential to our theme of visualizing this topology, because this is what distinguishes these shapes from each other when they could really take on much of any form. And so when you think about it, we're visualizing math here. And we're visualizing math, but what we're doing is we're using these numbers to kind of categorize these solids. So in the end, what we're doing is we're using math to visualize math, which I think is pretty funny. All right. So theme 3 is kind of extra, but I wanted to kind of explore the theme of infinity in your hand. And the central idea to in this theme of infinity in your hand is the disconnect that we have between our reality and the theoretics of math. And what I wanted to do is I kind of wanted to take objects that really only exist in theory, such as the Mobius loop, and I wanted to kind of bring them down, and I wanted to create physical representations of these solids that you could touch. So for example, this is a Mobius loop, and the idea behind a Mobius loop is that it's got a single never-ending surface. So if I wanted to, I could run my finger across the sides, and I would touch every part of this kind of runway, and it would just go on forever with no end and no beginning. And the Klein bottle, however, takes a little more of your imagination to think about. And the Klein bottle is a representation of a representation of a representation. which is kind of funny to think about, because what a Klein bottle is when you see, because this Klein bottle on this screen right here, this is a three-dimensional representation of a four-dimensional solid with only one surface. So what I did is I made a representation of that. But we find, actually, let me explain this first. So if you think about it, like I said, it takes some imagination. But what we're going to do is we're kind of run our finger over the side, up the loop, over on the outside of this neck. And what we're going to kind of do is we're going to almost just surpass this, this wall, and we're going to continue out. And we're going to come out through the bottom, and we're going to, we're going to come out and in, and then through the inside of the bottle, and then back out, and it just goes on forever. Like I said, it takes some imagination to think about, because going through walls isn't something that we really think about all the time in our reality. And so, what I found when creating these objects was that, yeah, they're cool, and they represent their mathematical, theoretical ideas. And I really created these as an aid to looking at a Mobius or a Klein bottle. I created this so that I could help you or help myself kind of think about what a Klein bottle is. But this disconnect between the reality and theoretical, kind of made me realize this isn't a Klein bottle. I had to cut a lot of corners to make this look kind of like a Klein bottle, which means it's definitely not a Klein bottle. And when thinking about this, I kind of realized, like, actually, the math is really more of an aid to the visual. And that kind of puts like a spin on the theme of our conference, visualizing math. But really what we're doing is we're visualizing our reality with math, which I think is pretty interesting. So, the goal of today was I wanted to talk about a few themes in topology using my pieces and how we can kind of visualize them and use them to teach different ideas. And then, something that topology is commonly referred to is rubber sheet geometry, because of the idea we have that we can stretch and contort different solids into whatever we want. And I always kind of thought this was interesting, or Dr. Cox and I thought this was interesting because, when I'm throwing these pieces on the wheel, they are very much rubber, and I can stretch them and I can contort them into really whatever I want. And if I have to happen to make a mistake, I can easily fix it. But through the drying process, and once it's fired twice, these pieces are clearly not rubber, and they will shatter if I drop them on the ground. And this opens another disconnect between kind of what I'm trying to show, what I'm trying to teach you with these, and the actual idea itself. The fact that nothing on this table is even close to being an actual representation of what it's supposed to mean in topology. That's kind of sad, but we can close that disconnect when we pair this with the design to make it accessible, the math to give it reality, and the art to make it meaningful, and the education to make it accessible. Thanks.
How hard would it be for you to show them the video of you throwing the torus? If it would be too hard, that's okay, but...
I don't know. Mason's got my phone.
Oh, so no.
Yeah, if you want, I can show it to you after. If anyone wants to see the video of me throwing a torus, I can show you after.
Can you tweet it?
I only have like 4 followers on Twitter.
Oh, you can use the hashtag. Anyway, I will stop dominating questions.
Well, that's it. You guys are welcome to come up here and look at them, touch them, feel them.
You should ask for questions.
I do. Questions?
Well, I don't know what to ask.
So I don't know where you are, in your career, if you're junior, senior, or
I'm a sophomore.
sophomore. Oh, okay, so you still got it, but, well, I was just curious, you had your 4 different routes of math professor, math ed, design, or sculpture. Which route do you think you'll go, or in your career? Maybe it's too early.
I have no idea. Hopefully somewhere I can do all of them. But I guess that's pretty small. Will.
From beginning to end, from throwing them on the wheel to glazing and firing them, how long did it take you to make all the pieces on the table?
Great question. So this conference came up, the idea of this conference came up, I think, in April, maybe? April. And I feel like I was told this was going to be in like November. So I showed up in August, and like I was like literally the day before I was going to leave for Miami, I got an email from Dr. Cox saying, "Oh, conference on the 21st. Is it 21st? Yeah, the 21st. Be ready." And so I had to make all this in essentially 3 weeks, which was really, really hard because I literally was like in the studio like every weekend until like 4 in the morning making these things.
So mean.
And what you'll see if you look at these closely is something I don't want to advertise, is that I had to like forcibly dry these so I could put them in the kiln I had fired them last Monday in the bisque, and I glaze fired them over Wednesday, and then cooled Thursday, unloaded Thursday night. But you'll see when forcibly drying, some of them like cracked, which made me really angry. But obviously it's a display case, so really this was supposed to look like this, but I couldn't just have this huge crack, so I flipped it over. But you'll see that there's cracks on other of these pieces, which, like I said, is not something that I wanted. It's like about 3 weeks. Any other questions?
Yeah, I was going to say, first of all, they're beautiful, and I think they really are both mathematics and art. If sometimes people in my work say to me, "Is that math or is that art?" And the answer is yes, it's both, and this very much has that character. I was going to say there is a mathematical art exhibit every year at the Bridges Conference, and you should consider entering these. I mean, it's a juried exhibit, but I'm familiar with what's there, and I think this is very worthy, and it has rich mathematical content. And I was going to say that there's many topology books. I don't know if you're looking for other models, but there's things like, I don't know if you like the figure 8 Klein bottle. There's another way of making a Klein bottle, not as familiar as this one. If you take like a figure 8 shape and imagine rotating that around to make a kind of a donut with it, but as it rotates, it also twists half a revolution. So by the time it goes around, what was the top is now the bottom. If you can try and visualize that.
So it's like a Mobius loop and a Klein bottle.
Yeah, exactly. Which anyway, it ends up having the same topology. It's homeomorphic to the Klein bottle you have. But anyway, it's a lovely shape, and people are less familiar with it. So if one of your goals is to make mathematical models that introduce people to sort of fun and interesting mathematical things, it's a shape that you might want to look at if you're looking at a challenge for future work, that sort of thing. Because you should keep going.
Last time anybody said to Kevin, "Hey, your work reminds me of, you should try," I got an email at like 5:30 the next morning. Told you I'd make it. So I'm guessing I'll probably take you up on it.
I'll be happy to talk to you afterwards. Yeah. The other thing I was going to say, I'll just briefly mention, there's something called a 3-dimensional zoetrope, where you have a bunch of physical objects. It's often done on a big circle, imagine a bicycle wheel, and you put an object on where each spoke is, and then you time a strobe light to flash as you rotate it, so that you see each one at a time. So what you actually see is your object looks like it's morphing. Like your eye, the strobe light captures one, and then when the next one moves into place, it's time to capture the next one. And it's an eerie, very powerful thing because you can move your head and see it from all different sides, and different people can see it all at once. It really looks like a 3-dimensional object transforming. These would be perfect for a 3-dimensional zoetrope, if you can imagine how that works. I mean, you look online, 3D zoetrope, and you'll see examples of different ways people have made them.
That's crazy. Any other questions? Zach?
As a pre-service teacher, trying to fulfill the math education block of this thing, use ceramics here. Could you think of any, or any of us, could we brainstorm any alternative materials to make them more accessible in like a classroom setting, so that they're not as necessarily as fragile?
Definitely 3D printing. It wouldn't look as cool, but you could definitely 3D print these. It wouldn't be hard. You can 3D print anything. I know I didn't make this up, but you can create a Mobius loop if you just like tear a strip of paper and like kind of twist it 180 degrees and tape it together, and you got Mobius loop. Other than 3D printing and ceramics and maybe like plastic molds, I can't think of any other ways.
I'm talking tomorrow, but I crocheted a Mobius or a Klein bottom.
Oh, no way.
So like Play-Doh would not work?
What?
Play-Doh?
Plasticine?
Play-Doh could work, I guess. I guess it could work because in topology, it doesn't matter if it's stretched out or anything. It doesn't need to be perfect like kind of these things look appear to be.
Cheap.
Cheap, yeah. This wasn't cheap. It's not my money I was using though. All right, well.
You're paying for the education, so you are paying for it in the slightest way.
Well, I've done the economics of my getting my money's worth in the science department, and I think I definitely get my money's worth. If there's no other questions, you guys are welcome to look at them, feel them. If you break them, it's not that big of a deal. I can make some. You'll see there's plenty of imperfections in here that I don't like. So I might just remake it, but it wouldn't work.
This is the easiest presentation I've ever given.
So which one is your favorite, Kim? Which
What?
one is your favorite?
In what terms of like how it turned out?
I mean, I don't know, in any way. You most proud of, or do you wonder, or?
Well, the Infinity one had no problem, had no issues, so that one's probably had no firing issues. So that was probably the best. But I think the best looking is the sphere double torus. By the way, Doctor, do you guys see yourself?
Okay, I was wondering.